Our Milky Way galaxy is staggeringly vast. Based on data from the Kepler space mission, astronomers estimate there could be up to 40 billion Earth-sized planets orbiting within the habitable zones of their stars. This volume of candidates forces a difficult question. Are planets like ours common, or does the exact recipe for life mean we are completely alone? To find the answer, we have to recognize that Earth-sized does not equal Earth-like. Our own solar system has repeatedly taught us that a rocky planet is rarely an inviting world. For decades, leading astronomers looked through early telescopes at Mars and imagined a relatively hospitable desert environment, complete with seasonal changes and water channels. Early space probes like Mariner and Viking quickly corrected that view, sending back images of a freezing, cratered wasteland completely devoid of surface water. Venus presented a similar disappointment. Scientists once hypothesized that its thick clouds hid a humid, tropical ocean. Instead, Soviet probes survived only briefly before succumbing to a toxic pressure cooker, where temperatures easily melt lead. Finding a true twin to Earth requires stripping away our optimistic assumptions. We have to apply an uncompromising multi-step filter to billions of astronomical data points to separate the dead rocks from the habitable worlds. The first filter we apply is density. We have to prove a candidate is actually a solid terrestrial planet, rather than a miniature gas giant like Neptune. The transit method measures starlight dips to calculate planet radius. Radial velocity measures the star's wobble to find mass. Together, they reveal density. Candidates must fall between half and twice Earth's radius. Anything larger retains a hostile gas envelope. Passing this test guarantees a solid surface to stand on. But a rock drifting in deep space is useless for biology if it is baking in radiation or frozen solid. This brings us to the second filter, the circumstellar habitable zone. This is the precise organal distance where a planet receives just enough energy for water to exist as a liquid on its surface. The location of this safe zone is dictated entirely by the temperature and classification of the host star. Most stars in our galaxy are red dwarfs, dim, cool stars that require their planets to huddle incredibly close just to stay warm enough for liquid water. Orbiting a red dwarf tightly causes tidal locking. One hemisphere is permanently cooked, the other frozen in eternal darkness. This creates an eyeball planet. A narrow ring of melted water is surrounded by a global glacier, an extreme climate that precludes complex life. Replicating Earth's environmental stability requires a habitable orbit around a sun-like star. We are left with the final, most difficult filter, proving that a rocky planet, perfectly positioned around a sun-like star, actually possesses liquid water. Finding out requires specialized observation. Next-generation tools, like the proposed Habitable Worlds Observatory, are designed to block blinding starlight and hunt specifically for oceanic signatures. When starlight hits a rocky surface, it creates a scattered, diffuse reflection. Liquids have a smooth surface acting like a mirror, known as specular reflection. At specific angles, a massive alien ocean bounces light uniformly, flashing a detectable glint to our telescopes. Capturing this mirror-like flash provides the physical confirmation required to identify a candidate as a liquid-bearing world. Detecting specular reflection moves our understanding beyond abstract data graphs and into the realm of physical surface features. Large bodies of surface water suggest a more temperate and stable climate, providing the essential medium for life as we know it to potentially arise. The search for Earth 2.0 has moved out of the realm of philosophy and into an active engineering timeline. The tools are being built right now, meaning the first human to see the glint of an alien ocean is likely already alive.